Hello everyone, welcome to the numerical methods class. In this class we are going to learn about interpolation but with Lagrange polynomials, which is different from the previous chapter. In chapter 15 we saw the interpolation with Newton polynomials, but now in chapter 16 we have Lagrange polynomials to have the interpolation. Let's see how this works in the following slides. Let's remember the Newton polynomial initially. If you remember, in the Newton polynomials, we have such a function as you can see here, and in this function we have some derivatives in first order, second order, and nth order, we can say. And we have some data, 2 data for the first one, for the second one we have 3 data, etc. And instead of this, we want to avoid the divided differences, these differences or the derivatives, let's say. We want to avoid them. And by reformulating this, we are having such a function as you can see here, which is a summation of some L functions and the fxi values, the function values of the data that we have initially. So these L functions are called the Lagrange terms, and these Lagrange terms are shown like this as a product of these differences. So these are kind of the finite differences, but shortened to be able to have a summation of some multiplication of Lagrange terms by the function terms. And this is called the Lagrange polynomial. And this pi sign, the big pi sign, represents the product of this, we can say. And if we think of the linear interpolation, which means we have an interpolation and with n equals 1, order of 1, this Lagrange polynomial becomes x minus x1, x0 minus x1 here, because n is 1, and multiplied by fx0 because I is initially, here I is initially 0 and n is 1 actually. From 0 to 1, that means we will have another term, x1, and in this again we will have x minus x0 because this has to be different from I. If I is 1, this should be 0. If I is 0, this should be 1. Then x1 minus xi, you can see here. So this kind of summation is coming from here by writing n equals 1. And this is called the linear version of the interpolation. And these are the Lagrange terms obtained from here. Let's see the quadratic version. In this, now we have n equals 2. In this scenario, here we have n equals 2, so I starts from 0 to 2, which means we have 3 terms, 0, 1, and 2 for fxi. And for Li, we have 1, 2, 0 for I as well. I is 0, 1, 2, and if it is 0, then this should be a different one, x0 minus x1 here, and also x0 minus x2 here. So this product comes into place when we have more than 2 differences for I and j. You can see here x0, this is I, and there are 2 data different from I, because for quadratic version we need 3 data, x0, x1, and x2. So x0 is this, and x1 and x2 are the subtraction from that. And at the top we have j, and that should be different from I as well. If I is 0, then this should be 1 and 2. In the second term, I is 1, so the j terms should be 0 and 2, simply. And for the third term, I is 2, that's why j should be different from that, and it should be 0 and 1, it cannot be 3. And there is no other term, so these are the terms, and these are the Lagrange terms for quadratic version, and this is called the Lagrange polynomial with quadratic degree, let's say, n equals 2. Let's check the Lagrange term properties. Each Lagrange term, given as the product of these terms, will be 1 at x equals xi and 0 at all other points. And if we give an example of quadratic version n equals 2, you can see here we had 3 terms. We mentioned this in the previous slide. And on the right hand side you have an example, and in this example this is the real function, and we have 3 data. x0 is 15 and the value is here, x1 is 20, and x2 is 25, let's say. maybe we can say this is x0, x1, and x2. So we have three terms, sorry, three data. This one, and this one. And if you check, we have three terms here. And in the first term, we have the function value of x0. fx0 is here. Like this. fx0. This is fx1. And this is fx2. So this equation shows that each of the three terms here passes through one of the data point and is 0 at the other two. So if you check here, this first term should be passing through fx0. So this one, you can see here, is the first term. This term, it is passing through 15 and fx0 here. But in other values, for fx1 and fx2, it should be passing through 0. Here, for 20, it's passing through 0. For 25 also, it's passing through 0. You can see here. For the second term, it's the same. It should be passing through from fx1 here. And for the other two, this is the second term. From 15, it should be passing from 0. For 25, it should be passing from 0 as well. So it becomes like this. And the third term, if we plot the third term, it is like this, and it is passing through the fx2 value for x2 here. But for the other terms, x1 and x0, actually, the function value, y value should be 0 here and here. So this is the third term. And if you plot these and combine these points, you will get an interpolation like this, basically, using this formulation. And so each product, Lix times fxi, takes on the value of fxi at the sample point xi. You can see here the first term is taking the sample point here for the 0 to x0, and for x1 the second term here, and for the third term x2 here. And this is true for lower orders and higher orders as well. So you can repeat a similar procedure by yourself if you want to. This is just an example for quadratic version. We will solve an example to see how the Lagrange interpolation polynomials can be used for interpolation. And in here we have a data on the right hand side with three axes and function values of these. And we want to use a second order and also first order Lagrange interpolation polynomials. And these data are coming from the ln function, the logarithm, natural logarithm. And we want to find the value of 2, actually ln2. And so x will be 2, and we want to find the result of it. So here, if x is 2, what is fx or f2? For the solution, let's start with first order. And let's see the Lagrange polynomial first. This was the product of this. And for the first order, if we want to open it by using this, actually we have two terms. We said this already. This is the formulation. That means we will use two data, x1 and x0. So we can use 1 and 4. Or if you want to use 4 and 6, it's possible too, but it's better to have a value covering this, the x value for which we want to find the function value. So 1 and 4 is in the range of 2. So 2 is actually within the range of 1 and 4. So that's a good idea to choose 1 and 4. Or you can also choose 1 and 6. 2 is still in between. So it becomes interpolation if it is in between. But if you choose 4 and 6, 2 is outside of the range. So interpolation result will not be very good because it will be an extrapolation now. And let's start with first order. So x is 2 and x1 is 4 and x0 is 1. If we write them all, as you can see here, and fx0 is 0 and fx1 is this value here, the result is this value for f2. So we simply found the f2 value as 0.46, and it's in between these, so that makes sense. And this is the same value as that we calculated for linear Newton's polynomial in example 15.1. You can go back to chapter 15 and to example 15.1 to compare the results. So basically the Lagrange polynomial is just an alternative solution, but it gives the same result with the Newton's polynomial if the orders are the same. Let's solve with the second order as well. And for the second order, we have this formulation that we obtain from the Lagrange polynomials and multiplication of 3 data this time. So we are using all this data now. We need 3 data. If we write them all in here, you can see the result here. I'm not going to talk about the details of these. You can stop the video and check the results or solve yourself. Let me just show fx0 is 0 here. fx1 is 138 here. And fx2 is 1.79 here, and the result is 0.5658444. And this result also is the same as the value calculated for quadratic Newton's polynomial in example 15.2. If you go back to chapter 15 and to example 15.2, we used the Newton's polynomial with the second order formulation and obtained the same result. So basically, again, the Lagrange interpolation polynomials are an alternative which gives the same solution if the orders of the Newton's polynomial and Lagrange polynomial is the same. So this is a good example to make a comparison for you as well.